All right, good morning, everybody. Hope you're all doing well. Today's lecture is going to be broken down into a few smaller pieces, and I'm going to be starting with 2D arrays. And we're going to particularly focus on how they're represented in memory. All right, I'm not going to discuss motivation, why you would ever care to make one. Just one example, they're frequently used to represent matrices in algebra. Oh, I just said I wasn't going to do that. All right. Anyway, declaring a 2D array is very similar to just declaring a 1D array. I've got an example right here, int a, and then I just need two dimensions, one for each of them. And in this case, the first element is going to represent how many rows we have, and you can think of the second one as representing how many columns they have. Okay, so declaration is pretty straightforward. Then from there, if I wanted to initialize this, I'm going to use something like a double for loop. I didn't get my indentation right in PowerPoint. All right, I'll go back and fix that for the slides when I post them online. Anyway, so I just did double loop and array access. Got my pointer right here. A, and then bracket I, bracket J. In this case, I'm just filling them in with 0, 1, 2, 3, and then row 2 will be a 1, 1, 1, 1, 2. Just using a math formula like this. That way we can kind of see in matrix notation, this would be right here, this would be row 1, column 2, assuming we've got a 0 indexed system. Okay, so now I want to focus on how these are represented in memory. I went ahead and went back and added the leading 0 for these so we can see that this is row 0. And then if I've got a chunk of memory, let's just suppose that it starts at hex address 1000. What's really going on when I store this 2D array in memory? And the answer is it just goes across and reads each row one at a time. So the first element is 0, 0, and then the second element in that first row is 0, 1, and then 0, 2, 0, 3, 0, 4. And then it just wraps around to the second row and just keeps on going. So the difficulty here is that memory in a computer is a one-dimensional array of bytes, everything with its own address. But in a 2D array, I've got two dimensions I need to worry about. So when we were trying to print out a 1D array, really the only thing we needed to know was the size of the array and how far down we needed to jump. So each of these is an integer in C, so they're going to be 4 bytes. So if I want to print out the 0, 2 right here, that's 2 elements down. The compiler just needed to figure out that I was looking for element 0x 1008 in this case for element 2. So, but printing out a 2D array, so I've got my initialization here. I've added some more code. If I'm using a function like this, void print array, and then I'm passing in an array, with a one-dimensional array, all I needed was the bracket. I didn't need to know, single bracket. In this case, I'll need 2 brackets. And then here's the code for that. And somewhere in there, there's going to be a double loop just like this one. And at some point, I'll be printing out element 1, 2. All right, so the question I want to ask is, how does the compiler know where to get that element? It's right here, 1, 2. And what I'd like you guys to do is pause the video right now and just get a quick review. Please compute the actual address of element 1, 2 right here in hex. So a little bit of review, and then we'll come back and talk about how the compiler actually gets to that address. All right, pause the video now. All right, welcome back. So I went ahead and added all these addresses in. They're 4 bytes apart, so 1000, 1004, 1008, and then 1000C, 1010, 1014, 1018, and 1001C right there to get element 1, 2. All right, so let's see, where was I? If I'm printing out this line, the element of this 101C. Okay, so now I want to go back and focus on the question, how does the compiler know how to do this? If we just had a one-dimensional array, I developed this formula last time. Where's my pointer? So inside the parentheses here, we need the starting address. And the starting address, I've decided it was 1000. Just for my example, it makes the math a little easier. And then we needed to know how many elements we were going to offset into this array. And then we needed to know the size of an integer. If we're typing this into the compiler, C already knows that this is an integer array, and it's going to take care of the size for us. That way, if I change machines and I've got a different size of an integer, I don't have to change my code. C will just take care of that formally. So what I'd like you guys to do now is just pause the video again, think of this as a guided learning opportunity today, and see if you can develop a similar formula for a two-dimensional array. And we'll do this in 2 steps. We'll start, what is the formula for just getting element 1, 2 from a two-dimensional array, and then we'll do a generic version. All right, so pause the video now and figure that out, and then I'll be right back with the solution. All right, welcome back. So the formula I developed looks something like this. I still need the starting address. And then I did this in 2 pieces. First, I need to jump down to at least this part right here where I start the second row. There are 5 elements, 5 columns in each row. And then I'm jumping down to row 1. So if I were looking at something in the top row here, this would be a 0. I'm looking at row 1, so I need to jump down by 5 elements, 1, 2, 3, 4, 5, to get to this starting address right there. And then each of these are 4 bytes, and I'm assuming the size of an integer is 4 for this example. Then I need to move over by 2 more places. So this is my 2 right there to go 1, 2 to get to the 12. And then again, these are each 4 bytes. So, all right, just to work this out to get the address in hexadecimal, I'm going to have a plus, here I just copied the formula again, I moved it up a little bit. The 5 times 1 times 4 is 20, and then the 2 times 4 is 8, so that's 28 in decimal. If we convert that to hex, we get 1c. So to do that, just quick review, I would take my 28, divide by 16, and that's where I'm going to get the 1 from. And I'm going to have a remainder of 12. And 12 is C in hex, so 10 would be A, 11 would be B, 12 would be C. And then when I add these together, hexadecimal 1000 plus hexadecimal 1b is just 10 1c. And again, I'm going to need to dereference this because I want to print the value. There it is, not the address. So that star says take whatever is in the address and go get the number. All right, now I want to ask another question. Does the compiler actually know that there are 3 rows and 5 columns? If I'm using a function like this one up here in the second line, void print array int a bracket bracket, anywhere, do we tell it that there are 3 rows and 5 columns in this array? The answer is no. In fact, I need that 5 right there so I can compute the actual address. I need to know that I'm going to be offsetting by 1 complete row and then moving down 2 more elements. So we need a way to provide that 5 to the compiler. It's pretty straightforward. Oh yeah, it's missing the 5 columns number. All we need to do is put the 5 in our function prototype and function definition. So both of those places will need a 5 so we can tell the compiler that this array has 5 members right here. And those need to match. If they don't match, it'll throw an error. All right. Oh yeah, the 3 for the number of rows is optional. The compiler doesn't actually need this and just ignores it if we put it in. Yeah, it's just going to assume that I have an array that's larger than this with more than 3 rows. And if I try and access those, it'll just be out of bounds elements that aren't actually filled in. And in C, for efficiency, there's absolutely no bounds checking. It's not even going to give me a warning or an error if I try and do that. All right, so really common question that programmers new to C have is, where does that 5 come from? How do we know that we need to put a 5 right there? And the answer is, it's up to the programmer to know the size of the array. C assumes that all of the programmers out there are experts. This language was designed to write operating systems and advanced software technology. And so a lot of that responsibility for checking things, for knowing how big they are, falls to the programmer. And I just want to point out that a really great way to do this is to use these hash-defined constants, compiler directive, that the precompiler is going to go and take anywhere that this word appears in the code and replace it with a 3. So up here, instead of the 3, I would put in max row, and instead of the 5, I would put in max column. This gives me a way to be consistent throughout the code. I don't have to hard code any numbers, and I can just have all of these defined up at the top of my file so that my code knows to use them. All right, before I move into my demonstrations, I want to just introduce the idea of multi-dimensional arrays beyond just 2 dimensions. And multi-dimensional arrays in C require that we provide our functions with all but the first dimension. With the first dimension, it can just compute an offset based on whatever it is, and if it happens to be in bounds, that's awesome. So in this example, if I'm creating a character array with, in this case, like a matrix with 3 rows, 5 columns, and then I want to represent these numbers as a string instead of the integers, then I'll need 3 characters for the dimensions I've got right here. So I'll need the first element, the second element, and then that \0 to terminate the string. If I initialize that and then call my print array function, I need to know these last 2. I need to know there are 5 rows and 3 characters per element. And then this one is optional. If I put it in, if I put the 3 there, it's totally fine. The compiler will not complain. If I leave it out, also fine. Alright guys, I've just jumped over onto a CSL machine and created a working directory for today's lecture. So far I've copied in 3 demo files. I've got the 2D array demo 1, demo 2, and demo 3. And let's just start out by taking a look at 2D array 1. When I change focus back to this screen. Okay, so what we've got here is a file that just is going to, if we start right here, I'm creating a matrix with max rows and max columns. Those are defined up here. Oh, before I get too far into this, go ahead, go to the Canvas site, download these files, follow along, and I'm going to make some changes, and then do your own experimentation. So there'll be time in between each demo. I'll tell you when I'm moving on, and you can pause and play with these a little bit. Maybe turn this into a 3-dimensional demo if you want. Okay, so here's the idea. I'm creating a matrix with max row and max column defined up here, and then I'm declaring some counter variables, and then I'll be going through each of these loops to just fill this in. Currently, this version fills in element ij with just the sum of those 2. We'll see what that looks like in a second. And then it's just going to print these out. So it goes through for I up to max row, so this will print the first row, and then it'll wait through all of the rows one at a time, and then it'll print out the first row, elements 1, 2, and 3. So printing that element, and then after it finishes printing the row, it'll print a new line. These are going to be separated by tabs. And yeah, let's go ahead and compile this and see what it looks like. So Q to quit, and then compiler command gcc-o for the output file, 2D array 1, and then input is 2D array 1.c. I need the M32, and let's see all the warnings. Alright, it compiles without any problem, just as is. And then, whoops, 2D array 1. We'll just go ahead and run this file. And there it is, it's printing out. So this is 0 plus 0, 0 plus 1, 0 plus 2 for row 0, and then columns 0, 1, 2. And then here, this is row 1, column 0, add those together to 1. So it looks good. Printed out exactly like I predicted it would. I got to thank Gerald for putting these together for me. Back when he was an employee at the University of Wisconsin, I just stole these directly. All right, I want to go ahead and just make a few changes. So this doesn't exactly match what I did in the lecture slides. I did steal it from someone else. So let's go ahead and we'll change this to 5 columns. Still got the I and J. I'm still going to do all of this stuff. What I really want to do here, though, is I times 10 plus J, so that it's giving me these, basically the row column index as my elements. And I think that's all I need to do to upgrade that. So we'll right quit, we'll compile, and we'll run it. Yes, that looks good to me. So I've got row 0 is going to be element 0, 1, 2, 3, 4. This should be 0, 0, 0, 1, the way I did it in my demo. And then row 1, element 0, row 1, element 1. Yeah, that looks good to me. All right, so go ahead. I'm going to move on to my second demo. I recommend you guys pause the video here. Think about any questions you might have, maybe an experiment, and go ahead and try this out. One other little detail before I do that, while I'm thinking about it. So in the demo I did for the lecture slides, I was using a function to print out the matrix. And here I'm just doing it right in the code. So I don't actually need to give this function the size. It's right here. So in this, the stack frame for main, it already has the information it needs to know that the max number of columns is 5 in this example. All right, I'm going to pause the recording, go pull up my second example, get that ready to go, and be right back. I've got my next example ready to go. I'm going to be looking at 2D array 2.c, that one. So let me get started here. We need a, there we go. So I've made some changes from the file that's displayed. I wanted it all to fit on the screen for my video. I've done this but similarly to the last one where I had my counter variables declared separate, and I've got all the brackets in for everything for good style, but then it didn't fit on the screen, so I removed them for the video. So it'll be slightly different when you guys download this to get started. So here's the idea. Here's what we're looking at in this demo is I actually want to talk about the memory addresses where things are stored in an array. This is just a way that you can go through and verify for yourself that what I told you in the PowerPoint is actually correct. So here's the idea. I'm initializing another matrix. This one is size 3.3. It fits on the screen pretty well that way. And then, so I'm just going to go through, and again, this is the one that begins with the sum of the row and the column numbers, indices. Yeah. And then we're going to go through, it's going to print out the array. This is the same code from the last file. But then we're going to go through each of the elements. This is going to go through I is 0 through max row, J up to max column. And then it's going to print out the address of, so this part right here prints the address of each of the elements in this two-dimensional array. So ij. And then we're going to print out I, so that's that number right there, which is I right there. And then we'll print j, which is going to represent that value right there. So there's j. And then we'll print out the value that's actually stored at that address. So this one is the address of operator, and this is the actual value stored in the array. All right, let's go take a look at this when we run it. So we'll get out of here, and then I need to compile this. So Control R, history, GCC, there it is. That's the line I used. So compile successfully, and then we need to run this 2D array 2. All right, so just like before, I'm printing out this array where these are the sums of the elements. So this one right here is row 1, column 1. Add those together, we get a 2. All right, now this is the part I really want to look at. So the starting address of my array, element 0, 0 of the array, stored at this particular memory location right here. Much more complicated than the PowerPoint demo. Got a lot more hex digits in there. What we can see is that they're offset by, so if we go from D8, 4 bytes down, 9, A, B, C is going to be DC. 4 bytes down from there is, so C will be E, D, F, and then 0. And that's going to upgrade the D to an E, and so on. So they're 4 bytes apart. And as I go through and I increment J, so 0, 1, 2, that's the order they're going in. When I get to the next row, so 8, C0, 4, 8, C0, 4, 8. That's how you count by 4s in hex. Yeah, then we have upgraded the row. See if I can highlight that to row 1 and then to row 2. All right, I am going to go back and change this just a little bit, and I encourage you guys to do the same thing. Let's see, where am I? I'm on this screen. So, hold on. Vim 2D array 2.c. Oops, oh dear. There's a 2 in here. 2.c. There we go. Okay, so I had a much bigger array. It was 5 columns. And then as I went through this, I also was using 10 times I plus j. So I was getting those row column indices. This should all be fine. This should all be fine. So just a minor change, and that should look like the PowerPoint demo. So right quit. We compile. And we run this. Okay, so there's the array I was using for the PowerPoint section of this. And we can see that to get to element 1, 2 is indeed 1, 2, 3, 4, 5, 6, 7, 8. 8 elements down. So that was offset of 7 from the beginning. So 5 for the first row, 20 bytes, and then an extra 8 bytes for to move over to position 2. And again, that's value 12. So let me just go ahead and put that in code and verify that in hex. So one sec. Go ahead and we'll edit this. Just one more little thing I want to print out before we return. So let's take the address of, we'll just store this in x. Int x equals address of matrix 1, 2. We'll subtract the address of matrix. All right, let's see what this looks like. So compile. Oops, format p expects an argument given a type void, but it's got to type int. All right, I'm gonna pause, go fix that. All right, got this fixed. So all I needed to do was change this p to a d, and now it's gonna print out the difference in locations. I'd forgotten that when I do this, C automatically takes care of the size of the integer, and it's just going to tell me how many positions they are different by when I subtract addresses of integers. So to actually see how many bytes we've moved, I have multiplied this by a size of int, just to verify that what I said in PowerPoint at the beginning of the lecture actually matches. So let me get out of here, and then we'll compile this. There's the compile command, we'll run that, and then we'll run this. Alright, I'm messing up. 2D array 2, there we go. Okay, so we see down at the bottom that the position of element 1, 2 is offset by 7 from the beginning. So here, let me count this way. 1, 2, 3, 4, 5, 6, 7. There's 1, 2. And because it's 7 elements away and integer is size 4, we can see that we're 28 bytes from the start of the array. So I encourage you guys to stop the video, go come up with an experiment to do to quiz yourself a little bit, and then come back for demo 3. Alright guys, I just pulled up my third example here in Vim. We can walk through this. This is the version that has a print 2D array function. This is going to take just one parameter, the matrix itself. I'm going to call this A here. To make this work, I don't need a parameter for the very first dimension, but all other dimensions, there's only 2 here, require that I put in a dimension. And I'm using max columns here. It's just good practice. It's a hash defined variable. So the pre-compiler will take this and copy and paste the 3 in there for me. Next up, it doesn't return anything that's void. And then just like the other code, it creates that array. This is the one that has the sum of the 2 elements as the entries. And then it's going to call this function that prints it out. This is the exact same code we've been using to print them out. It's just now encapsulated in a function that again has the same prototype as the line up there. So I'm going to quit this. We'll go back, compile it. So, yep, there it is. I'm compiling array 3. We'll run that, and then we'll print out array 3. There's a lot of garbage on the screen. There we go. So this is just using a function to print out the array. I want to do a couple of experiments though here. So I'm going to head back over to Vim. First thing I want to do, I want to print out the array I've been using all along. So replace that with, go back to Vim, replace that with a 5. Then down here, I'm just going to add times 10 and make sure this still works. So we'll compile again, and then we'll run it. Yeah, there we go. So now I've got the bigger array easily printed with a new function with just minor changes. The only thing that changed the size was that max columns. So let's go back. I want to do, come on, Mike, what are you doing? Oh, I'm getting some incredible lag here. My internet is not working very well. All right. There it is, Vim. I want to know what happens if I change this max columns to something different. So instead of using the variable, I'm just going to hard code this. Let's put this in as insert 3, wait for the lag. There it is. Over here, I'm going to delete this word, and then insert a 3. All right, there we go. So these two have to match, otherwise the compiler will, oh, let me show you that. So replace that with a 4. Now if they're different, now if I compile this again, compile this again without the garbage. Okay, yep. It's going to give me this first warning, passing argument 1 of print 2D array from incompatible pointer type. So it knows that this does not match int 5. Maybe I didn't change everything. Would print 2D array. Oh, did I get these wrong? Oh, I put in a, yeah, 3 and a 4. That's what I really wanted. Hold on a second. Let me take a look. I'm messing up. Let's get out of here. Clear. Compile. All right, let me see this warning. Passing 1 argument of print 2D array from incompatible pointer type. So it oh, this is a warning, right? So the warning says that it's got the matrix has a 5 here, and it expected int 3 because that's what's in the prototype, but the argument is different. Void print. Yep, there it is. It's giving me the prototype. And then here, this is the real error that it gives, conflicting types for print 2D array. So the prototype has a 4 in it, and the actual definition has a 3. I think I reversed those. Definition has a 4, prototype has a 3. Okay, so if I didn't have this all warnings turned on, this first part would not have printed. And this is the actual error. So basically it's just telling me that these don't match. So let's go back and change that. So there it is. And I just want to know what happens if I'm using a completely inappropriate size. So we'll change that back to 3. So this does not match what's in the array. We'll compile it. It's still going to give me that warning because the more modern compilers with all the warnings turned on recognize that this array is of different size. But now I don't have any compiler error. So it should run. If I can find the... There we go. Interesting. This experiment didn't do exactly what I was expecting it to do. It's actually printed the array exactly as it's stored in memory. So let me go back. Wait, no, it hasn't. It hasn't. Hold on a second. Yeah, look carefully at the second row. So, well, let's start with the first row. So when we looked at the code, it's actually using a loop that goes from 0 up to max columns. So this first one is just fine. So I've stored the array in memory, just like I had been. So I've got 0, 1, 2, 3, 4. For this would be row 0, column 4. But then when I passed in that 3 as the parameter for how many things are in a row, it is only offset the element by 3. So it's going to go 0, 1, 2, and it thinks that's the entire first row, but then it's starting over here back at element, this would be the 4th one down in the matrix. And so it's printing 3, 4, and then the next row would have had the 10, 11, 12. And then instead of a 4, we should be looking at the, what is that, the 7th element? 1, 2, 3, 4, 5, 6. The 6th element, I believe. 6th element of the array here, because it thinks there's 3 in the first row, 3 in the second row, and then, well, offset by 6. So this is the 7th element. I did have that right the first time I said it. So 11, 12, 13, 14, and then the next one is 20. So when I put in an inappropriate value right here, it's choosing poorly where to look. All right, I'm going to jump back into PowerPoint and see if I can do a better job explaining that. Cancel PowerPoint, full screen. So here's what it's doing. This is my array as it's put into memory. I've got 0, 0, 0, 1, 0, 2, 0, and then the second row, 1, 0, 1, 1. But what it's doing when it printed out that first row is it's printing the 0, 0, 01, 02, 03, 04, just fine, because the loop inside goes from 0 to max columns. But then the function declaration has a 3 there, so it thinks that the next element's going to offset by 3. So 0, 1, 2, 3 elements, and then it thinks the next one is this 0, 3. And then 0, 4, 1, 0, 1, 1. I believe it went to 1, 2. But then for the third row, it's going to 1, 2, 3. It thinks that's the first row. 3, 4, 10, thinks that's the second row, and it's going to start right here and print 5 elements. 1, 1, 1, 2, 1, 3, 1, 4, and 2, 0. Let me jump back into Putty and just, yeah. So throw 11, 12, 13, 14, and 20. Okay, so I want you guys to just pause the video here, go to this code, and mess around changing those things and just kind of do a little experimenting. All right, and I'll be right back with my conclusion. All right, guys, I think this is one of those topics where getting the chance to actually go in, read the code, make some changes, and do some experiments, and be surprised by the results, and then take the time to figure out what's really going on is very valuable to understanding how these 2D arrays are stored in memory. And that's really the connection I wanted to get out of this. The take-home message is how things are stored in memory, and then how C is able to access those things with minimal information. Just as a reminder, we need to include all dimensions except the first, and it can figure out where to go in the matrix, because I need to know how many things are in a row, how many columns I have. So definitely, if you haven't done so yet, go back, get this code, and play with it. I think you're going to find that extremely valuable. Better than watching the lecture, better than reading the book, doing it yourself. The more time you guys spend with this information in your brain, experimenting and trying to figure it out, the better you'll learn this stuff. All right, so I'm going to go edit this video, put it up on YouTube, and then I'm going to record the second video for today. All right, I'll see you in a little while.